So tonight's event is about celebrating the young people that we work with or see from a distance, perhaps whenever we're at conferences. And tonight we've got 4 students from the University of Sheffield and from Sheffield Hallam who are going to be presenting a materials story, so something that they do research on or have an interest in. They've got 15 minutes to deliver a presentation. If they go over or under their 15 minutes, they will be penalised with regard to the marks. And we've got 3 judges. So we've got Sarah Hinton from Autocompany. We've got Peter Morgan. I'm pointing them to them on my screen, but you guys can see them on your screen. Peter Morgan's our SMEA representative and has been judging these competitions for at least as long as I've been involved, which is about 4 years. And I know that that history goes back much further. And we also have Evangelos from Sheffield Hallam with us tonight as well. So these 3 already have experience in materials, and I'm going to ask them to give a quick introduction about what their expertise is. So once all of the contestants have, let me rephrase that. Once the contestant has finished their presentation, each judge will ask them 1 question, and then we'll move on to the next contestant. Once all 4 have finished their presentations, the judges will move into a breakout room where they will discuss who the winner is going to be. And at that point, you guys can ask our contestants questions using the chat box, or you'll be able to raise your hand, turn on your video if you like, and ask your question directly to a contestant. We're going to spend only about 5 to 10 minutes on this. We expect the judges will need around 15 minutes at most. And one of the most important things that we'd like to do tonight is to celebrate some of the students from both universities who have won awards. So we've got 7 undergraduate students with us this evening. Whether or not they're all here yet, I'm not too sure, but we definitely have some of them. And we've got Mark Tomlinson and Andy Woods are going to do that student presentation at the end. And then our judges are going to come back and announce the winner. Gosh, the numbers are still climbing, guys. We're up to 40 participants here. No pressure to our contestants. So perhaps I'll hand over to our judges and start off with Sarah, if you'd like to unmute yourself and give us a little bit of information about where your expertise lie. Thank you.
Hello, my name's Sarah Hinton. Hopefully you can hear me okay. Okay, good. I'm a metallurgist working for Perovskite Stainless in Sheffield. So my field is alloy development, tailoring what we produce to our customers' needs. We are a melt shop, and so we produce about 250,000 tonnes of stainless steel a year. It goes all over the world. We use in everything from undersea pipelines to more prestigious buildings like the Burj Khalifa, for example. So, I'll be my sort of area is how we can use materials functionally. So everything that we do is sort of is very functional, very customer focused. So that's my area.
Excellent, thank you for that, Sarah. Peter, do you want to give us a quick update on you?
Okay, Peter Morgan, studied metallurgy at Sheffield University last century, spent a working life in the special steels industry in the Sheffield area, so Stocksbridge, Rotherham, etc., supplying steels to everything from aircraft, aerospace, to razor blades, to automotive, to power generation. So basically a special steels area. Retired some time ago, but still heavily involved in SMEA. And when allowed, we are doing promotion to schools of material science and engineering, but unfortunately we've not done much in the last year, but we have got some ideas going forward. That's me.
Brilliant, thank you, Peter. All right, who's am I looking for now? Evangelos, hi there.
Hello, I'm Evangelos. My name is difficult to pronounce, I assume. I'm from Greece, that's why. I'm course leader for the BEng and Men's Materials Engineering courses at Sheffield Hallam University, and my expertise is in structural health monitoring of advanced materials. I spent a couple of years, I would say almost 10 years, with non-destructive evaluation techniques such as ultrasonics, infrared thermography, and acoustic methods, acoustic emission, mainly for composite materials, but I've expanded lately my research on dental materials and also for some memory alloys, and I'm now moving to more smart materials. So that's mainly my background and my expertise, my research expertise. Thank you.
Thank you, lovely to hear from you, and nice to have such a variety of expertise on the panel. So I've already mentioned we've got our 4 speakers. They're going to go in order of Mark, followed by Francis, then we've got Krishnand and Daniel. Okay, I assume our judges are ready. You've got the marking criteria handy, and you've got something to make notes on. Brilliant. Okay, just so everybody's aware, we've got over 45 people on the call. This is brilliant news. And Mark, I'm going to ask you to unmute yourself and then share your screen.
Right.
And of course, that means that everybody else should mute themselves. So if I need to, I will mute you from here.
Right, can you see and hear me?
Yes, Mark, it's all good. I'm going to turn myself off now. Bye.
Excellent, cheers. All right, so thanks everyone for attending. So my presentation will be aimed at just getting you to appreciate the ubiquitous components we use in the thousands pretty much every day. So the content covered here is a compilation of undergraduate lectures, personal research, and fun facts. And hopefully it'll be at a level that everyone can follow. So the title of my presentation may be somewhat technical, so let's start simple. What is a capacitor? So in its simplest form, it's an electronic device that can store energy in the form of charge. And it can then go on to release that energy when you need it and at the speed you need it, quite rapidly as well. It's much faster than a battery, but it can carry less energy than a similar sized battery can. So you can think about it, if you're into cars, you can think of capacitors as having higher acceleration and batteries as having a higher top speed, essentially. So how does it work? Well, 2 metal plates are electrically connected and they're separated by air. So there's a power source that kind of pushes electrons from one of the plates to the other. And that means there's a pileup of electrons on one plate, which means there's a negative plate, and that leaves positive charges on the other plate. And the electrons would ideally like to combine with the positive plate, but because there's air in between, which we know it's an insulator, so they can't really make that jump. And so an electrical field is created in between them. And if we then remove the battery and put an appliance in, the electrons, we've now just kind of given the electrons a way to recombine with those positive charges. And in doing so, they pass by the appliance and operate it, essentially, which is useful for us. So capacitors are used in a lot of everyday things. So this is just an epilepsy warning here. So if you're susceptible, I'll give you 3 seconds to just turn away, and I'll let you know when you can turn back. So 3, 2, 1. There's a flash camera snapping. So the time it takes between you hitting the button and the light to come out is the capacitor charging up. And then it's that fast release of light is essentially the capacitor, the electrons just coming back, essentially. Another application is the spark plug in car engines. So the air-fuel mixture comes in, as we can see, it gets compressed, and then the spark plug ignites the mixture, and it's that combustion that then can move your vehicle, essentially. But we don't live in a perfect world, so a high concentration of electrons, they're attracted to the positive plate. They would really like to go to that positive plate because we know positive and negative charges attract. And besides the attraction to the other plate, they also start to repel themselves on the negative plate. So essentially it's the attraction to the other plate as well as the negative repulsion in their own plate leads to what we call breakdown. So at some point you'd find that once the electrons get too close to each other, they really want to stay away from each other. They break down the air, so they will conduct through the air. It's called a breakdown field, and it's strong enough to turn the air from an insulator into a conductor. And that's what happens with lightning. So there's an accumulation of electrical charges in the clouds, and it's so negative that they really want to get away from each other. And so the Earth is treated as a positive, and then the electrons just have to go somewhere, so it just strikes through the air, Fun fact about lightning, it superheats the air around it to 30,000 degrees Celsius. So that's around 5 times the surface temperature of the sun. So there's a lot of energy in these electrons. So that's why they'd really like to get away from each other. Here's a kind of a real life example. So let me play that video. This is 2 electrodes, and there you go. That's essentially just very high potential that the electrons need to get away from each other, and yeah, the air just breaks down. Electrical breakdown isn't always very bad, so we put it to good use as well. So say you've got any household appliance, it's represented by the circuit to be protected symbol here on the right. So as we've seen, electrons can power appliances by passing through them and then kind of going back. So that's normal operation, what would happen. But then if you have a high voltage surge, usually a lot of appliances have this voltage dependent resistor component. This breaks down at high voltage. So essentially the electrons have a path of less resistance to go through. And by doing so, the high voltage is eliminated from passing through your appliance, essentially. So it's useful here, but it's not really useful for capacitors in this application. So still quite a big problem we need to solve. So scientists just have found through history that get something that can insulate better than air can. And that's kind of pretty logical. If air can't hold that amount of electrical charge, get something that can. And a polar material, it also enhances the response to the field. So polar just means there's a positive end and a negative end of the material. So that's our challenge, finding an electrically insulating material that has a more positive end and a more negative end. And in order to quantify how good materials are and compare them to each other, there's a permittivity term that scientists often use. So the higher permittivity of a material, the more charge it can store in these kind of capacitor applications. So let's talk about the ceramic that they've come up with. So the most common one is barium titanate. We do quite a lot of this in our undergraduate program. So dielectric just means it's the insulating material that's used. Barium titanate adopts what we call the perovskite crystal structure, which is shown on the right here. Each of the spheres represents an atom. So this is very small. A unit cell, which is what we call this, you stack a lot of these next to each other, and these make up your bulk material, essentially. So barium titanate, barium occupies your corner atoms, titanium occupies the middle of the cube in the center, and the oxygen occupies the 6 center faces of the cube. Now that you know about the ceramic, let's talk about the capacitor itself. So scientists, again, have found out just throughout the story of their development that instead of just having 2 plates, why not just stack a lot of plates next to each other? And that's what we can see here. So these, the thinner, whiter lines are essentially the electrodes or the plates, usually made out of nickel, but can be made out of other stuff as well. And they're alternating, and they're alternating at their termination, and that's how they get their positive and negative charges. And the darker, thicker sections is the ceramic in between. So there's an extremely high demand for capacitors, and the industry's growth is exceptional. So just the scale here, 2 trillion capacitors in 2015, and 2020, we expected 3 trillion capacitors to be sold. And indeed, despite the pandemic, because we don't really stop using electronic devices, 3 trillion capacitors were sold. So that's 150% growth. Just putting a scale, 3 trillion is 3 with 12 zeros behind it. So just in case, just to give you an idea of the magnitude. Global market is valued at above 10 billion. So very, very big. There's about like thousands of these in your phone, thousands in your laptop. What you're using to watch this presentation probably has over 1,000 as well. So in the previous slide, I showed you barium titanate was cubic. That's only true above 125. So there's more problems. I keep solving problems, but we face some more. It's under 125, it's tetragonal, which just means that one of the axes is longer than the other 2. In this case, it's the vertical. So because the axis is elongated, the titanium atom in the middle, it can offset when it's put under a field, so it has a positive charge. And so once we start putting it between the positive and the negative plate, that titanium atom really wants to attract to the negative plate. And that's what I've got on the left bottom image here. So imagine each of these is a unit cell, and as the titanium shifts up, you get like a slightly positively charged side and a negative charge, and that aligns within the 2 plates as shown. moving on, so I said it turns cubic at what we call it the Curie temperature. So the titanium atom can no longer offset, it is just stuck in the center, and that way the permittivity or the charge storing capability takes a sharp hit, which is not ideal. So what we'd like to do then, I'll just present you with some small results of a research project I did as part of the SURE scheme at university. Essentially, we want to control that Curie temperature to be able to push it up or down, and then understand more about how capacitors can operate at higher temperature. We'd ideally like consistent behavior without the peak you've seen. Not relaxers here refers to, there's an entire scientific field called ferroelectric relaxers, which aims to kind of relax that peak that we've seen before, just broaden that over a wider temperature range. But this isn't what we're trying to do with the presentation, with the research project. And this is useful for understanding how capacitors can perform at high temperatures, potentially for high temperature applications, like the car engine. I should mention that the spark plug does not use ceramic capacitors, it uses other types of capacitors. But I just thought to keep consistent with regards to applications. But in terms of pure ceramic capacitor applications, any electronic device in any industry will have these in the thousands. So these are just some examples on the left here. So how are we trying to control that Curie temperature? Well, we're adding foreign atoms into that barium titanate ceramic to try and see whether we can get a change in that Curie temperature, to see if we can push it up or down. And making the ceramic in different routes or different ways can also help us assess if the Curie temperature is affected. So now that we have a good background with the topic, the foreign atom that we've chosen was calcium. So 10% calcium dope just means that one calcium atom will replace 1 in every 10 barium atoms. Now calcium is smaller than barium, so I've just put the picture here so you can imagine if we replace that corner barium atom with a smaller calcium, that would distort the unit cell a bit, and therefore the unit cell would need kind of a different temperature to transition into cubic. And that energy difference is essentially that manifests as that temperature difference in the Curie temperature. So the two different manufacturing routes, this is called the solid state synthesis route, one without the calcining step, which is shown in the green arrows, and one, the longer route, includes the red loop as well. I don't need to dwell on this for long, but what you just need to know is the calcining step, which is top right bubble. Calcining just means putting it in an oven and just chemically reacting the species together. Sintering, which is in the middle of your screen, is just getting them into the physically required form, and that's also done through an oven. So we undertook both those two routes for two mixtures of powders, raw powders, and that's how we obtain them in nature, calcium carbonate, titanium oxide, barium carbonate, and mixed powders, just adding calcium and titanium to preformed barium titanate, essentially. So we did XRD results, XRD experiments, and the scans essentially show that they're equivalent. Pure barium titanate, obviously you expect to have different peaks, so there's some shift if you can see it, and beyond 60 there's other shifts as well. But what I really want to show with this slide is that they're essentially equivalent, and we are in theory testing the same material. With XRD as well, you can characterize these distances of the unit cell. So as discussed, calcium is a smaller atom, so we expect that the unit cell would be smaller. So we can see pure barium titanate has lattice parameters the biggest, and then as you add calcium to preformed barium titanate, that shrinks down, and then when you put calcium barium titanate together, that shrinks down even further. I should mention the units here are called angstroms, so that's the A with the small circle on top. So that's just, if you take 1 meter, divide it into 10 billion parts, 1 angstrom is one of those 10 billion. That's 1 followed by 10 zeros. So then how we then measure the electrical response is we put the ceramic in an oven and heat that oven at a rate of 1 degree per minute. And then we set up alternating currents, which just go from one direction to the next. They keep kind of reversing direction. And these scan through the ceramic pellet 500 times at different speeds. And because we had different samples, these differed in geometry. So the sizes of the samples would affect how much charge they can store. So in order to just effectively compare them and kind of account for the size difference, we multiply the permittivity by this geometrical feature of area over distance, sorry, and that gives us the capacitance, which is a better comparison quantity. So what we found is the graph on the right is just a zoomed in picture of the graph on the left. So pure barium titanate, as you can see, has the highest Curie temperature at just over 125. And as we add calcium, we start moving to the left. And I'll try and point your attention towards the red and the green are the ones with the calcination steps. And we can see that these have moved further to the left and have higher peaks. So essentially, this kind of proves how important the calcination step is. It just gives rise to more pronounced effects, essentially. So a larger decrease in the Curie temperature and a larger increase in permittivity as well. So this is kind of in just very briefly what was done for the research. And this is a very small part of the kind of industrial research that's going on. So this is a plot that has quite a lot of information. So I'll try and just focus your attention towards the transition temperature of 125 there, which is what we were trying to work on. And we were interested in the calcium substitution. So looking at the solid line. So as we can see, the more we add calcium, the transition temperature falls ever so slightly, which is what we saw with this plot essentially. And so in doing so, the cubic transition can be delayed or happens early, essentially, depending on what we want. So it's through introducing foreign atoms and making them in different ways that we can really utilize different kind of transition temperature relationships. And we are, as a result, more able to use capacitors in different temperature ranges. Thank you so much.
Brilliant. Thank you very much, Mark. Very interesting presentation, and I'm sure the judges will have some questions for you. Okay, perhaps I will go to Peter first.
Okay, yeah, very interesting. Capacitors are things we don't often think about, do we? You know, we look at a spark plug and you don't think there's a capacitor there, and all these other things. So there's lots of them around. There's millions of them. So quite fascinating, the hidden component that we didn't know about. A more general question, rather than going deep into the technical stuff, but what about the availability of materials? If these are, you know, there's so many capacitors required around the world, you're talking about barium titanate, wasn't it? Yeah, well, calcium doped version. I presume that's pretty available, is it? Is that, you know, manufacturing of this, is it pretty easy? And does that therefore make quite a cheap capacitor?
Right, thanks for your question, Peter. Well, actually, it's quite a developed process, you're right. So these, usually the main way of manufacturing these is called tape casting. In terms of the material supply, there's barium titanate in itself, there's no shortage in the materials that I'm aware of. But however, in terms of the industrial ones that we use, they do use rare earth elements. So in this research project, I just focused on calcium. But in terms of the actual industrial ones that would be in your phone and your laptop, etc., they use a lot of very, very rare elements, holmium, dysprosium, etc. And these are quite, I think they're on the critical raw materials list of the EU. So there's current research into trying and making them more sustainable, use more sustainable materials with more supply, essentially.
Okay, thank you. Great.
Thanks for your question.
Next question. Who's going? Sarah, you going to ask the next one?
Certainly will. Now, Peter was naughty there because he accidentally scuppered my question, but never mind, I have a backup. So when you were, very interesting, by the way, I also have never really thought of capacitors, it has to be said, but I did enjoy that.
Thank you.
In your slide about the multi-layer ceramic capacitors,
right.
I think you said that one of the components was usually made of nickel, but made of other stuff as well.
Yeah.
What other stuff?
Well, nickel is the most common base metal, but a lot of base metal electrodes are used. So copper is another example, but nickel is by far the most common one. Thanks for your question.
Okay, why is nickel the most common? What is there an inherent property that makes it beneficial?
Well, good question. I think it has preferred, well, I say preferred, better properties when we fire the ceramic. When we make the ceramic and then we include the electrodes or the plates in with it. So when we do that, nickel is less likely to get like redox reactions happening as opposed to other stuff, which makes it quite attractive, as well as conductivity, obviously.
Great, thanks.
I assume it's my turn now, isn't it? Can you hear me? Yes. Thanks for your presentation. It was very interesting. I'll go to a little bit more technical question. Sorry about that. My question is, why, first of all, you picked calcium and not any other element? And what is the minimum or the maximum percentage of doping that you can go for calcium? Because, okay, I don't know about the specific materials, but 10% seems a lot. I don't know.
Right. Yeah. Thanks for your question. So why did we choose calcium? Well, there's more that. So the research project involved more than what I'm presenting now. I presented a small part of the research project because it's relevant to this talk. But essentially, we were interested in finding out more about the barium titanate and the calcium titanate interface, the behavior of that interface between them. We thought that would be quite interesting. So that's another part that we tried to study as well. So it was kind of the main driver behind choosing calcium, but also because it's readily available and it was just easy for a summer-funded research project. And in terms of the amount of calcium doped, you're right. 10% may seem quite a lot. Usually for industrial capacitors, again, this kind of ties in with my answer to Peter. Because of the rare elements used, they use like very low amounts of holmium, dysprosium, etc., other rare elements. So the actual industrial capacitors that you would get don't have that such a high amount of dopants as this research project. This was just in order to get a measurable size effect in order to characterize our results. So as you saw from that last slide, the calcium decreases ever so slight. So we needed to have a certain amount in order to essentially measure the difference, if that makes sense.
Thank you.
Thanks for your question.
Thank you very much, Mark, and to the judges for those questions. Do feel free to pop any questions that you have into the chat box and we'll pick them up at the end once all of our speakers have spoken. Okay, who are we moving on to next? Find the tab. I think it's Francis. Yes. All right, Francis. Whenever you're ready, you can unmute yourself and share your screen. We can hear you.
There you go. Can you see that?
Yeah.
I just go to present. Right, so good evening, everyone. My name is Frances Lavera, and I'm a first-year PhD student at the University of Sheffield, and I'm also part of the Advanced Metallic Systems CDT. So my research for my PhD aims to improve the complementarity between two research topics I'm going to introduce you today, and these are additive manufacturing and brazing. So first up, I'd like to just show you what I'm running through. So I'll be introducing additive manufacturing, what it is and what brazing is, and then the benefits of combining the two techniques and the potential barriers to combining the techniques as well, and how these barriers might be turned into solutions or how else we could overcome them. So first up, what is additive manufacturing? It's essentially 3D printing by manufacturing a part layer by layer, and you can produce, you can produce some very complex shapes, as it has a greater dimensional freedom than conventional subtractive manufacturing techniques. And it's used in a variety of industries such as aerospace and medicine, and it's found applications within part production and selective repair, as well as the lightweighting of parts. So on the right-hand side of my slide, I've got an example of one type of additive manufacturing, which is called selective laser melting. And essentially what happens is the powder reservoir moves up as the build plate moves down. The powder spreader then doses the build plate with powder, and then the laser fires selectively on the areas where parts are being produced. The laser causes rapid melting and resolidification of the powder, and this creates a solid part. And as you can imagine from this, one of the real limitations of additive manufacturing is the size of the build plate. So you can only produce a part that will be able to fit on that build plate. And I realize this is quite an abstract concept, so I've just included this to show you what it's like in real life. So you've got the powder spreader at the very front of the image on the left, and the powder reservoir, then the build plate, which has the first layer of powder already on it, and then the overflow of the powder at the back. So any powder that isn't melted by the laser can be reclaimed and then sieved and reused in the future. And if I just play this video for you, you can see what it looks like in action. So the laser moves and only melts selective areas, and that's why it's called selective laser melting. And this can produce some really cool parts. So here's a selection of things that some people in my research group have been working on. And I included these images truly so you can grasp the freedom of the manufacturing method, where you can get quite complex geometries, especially in comparison to other manufacturing methods. So that's an overview of what additive manufacturing is. So now I'll move into introduce brazing. So brazing is a technique that's been around for thousands of years, and it involves the joining of two materials together using a filler metal at temperatures that are typically above 450 degrees C. So brazing has found a variety of applications, including fusion energy and nanoelectrics. And a particular advantage of brazing is that it can be used on dissimilar materials. So brazed joints are typically stronger and have better mechanical performance than soldered joints, and also have the brazed joints also have an advantage over welding, because welding typically can cause thermal distortions within the microstructure. However, brazed joints can be limited in terms of the simplicity of the joints that you can produce, as you can see on the right-hand side of my slide. And also the surface finish for a brazed joint to be effective is really quite smooth, so you really need to machine it down. In terms of the stages of brazing, it's a 6-stage process. First, you need to ensure that you've got a good joint design. You need to make sure that the base materials are cleaned for anything like oil or grease that might have been put on them during the manufacturing of the base materials. Then the oxides are removed with a flux. You then heat the base materials up to the required temperature for the brazing, and then introduce the filler metal typically, and this spreads through the joint via capillary action. And then the entire assembly is cooled and cleaned for any excess flux and such like. So a really important part of this is choosing the correct filler metal system for whatever application that you're needing it for. So the first core property that I'm going to tell you about is the melting range. So this is, it begins at the solidus temperature, which is represented by T3 and T4 in the image. And that's when the alloy will begin to melt, and it goes all the way through to the liquidus temperature, which are represented by T1 and T2. And that's where the alloy will become fully liquid. So this is really important for the specific application that you'll be needing a brazed alloy for, because you really don't want the filler to be melting in applications. And you can also see that T1 and T3 has a much wider melting range than the melting range between T4 and T2. The next of these core properties is the wetting behavior, and this is classically determined by the Young's equation, where an angle less than 90 degrees is wetting, and this is what we want, and an angle greater than 90 degrees is non-wetting. So you need to have a positive interaction between the material and the filler metal to ensure wetting, and therefore to ensure that a joint is formed. And you can have different types of wetting. So you can have reactive wetting or non-reactive wetting. And it's really important to consider what type of wetting you're going to be looking for, because reactive wetting itself can give an interaction zone which could cause undesirable effects, such as brittle intermetallics that would reduce the joint strength. Other factors that affect the wetting behavior are also things like surface roughness, cleanliness, and oxide presence. And the last of the core properties is the flow behavior. So filler metals move through a joint through capillary action. So the flow behavior is really important, and this is influenced by the melting range. And it also means that you can tailor a joint clearance based on the flow properties, or you can base which alloy you select on the clearance that you need. So a better flowing alloy would be better suited to a smaller clearance gap. So I've introduced additive manufacturing as a layer-by-layer manufacturing technique, as well as brazing, which is the joining of materials at high temperatures using a filler metal. So these are really important areas of research in their own right. However, what I'm really looking to do is increase their complementarity so that they can be used together. So I'm looking to join additive manufactured subcomponents, which might be limited by the size of the AM build plate, as I showed earlier, and do that using by brazing on a native additively manufactured surface, and then you get the benefits of both techniques. So why could this be important? So this could reduce the lead time of component manufacture compared to a multi-step subtractive manufacturing technique. It also reduces the wastage that is there currently, because at the moment any AM surface is machined down to create that smoother surface. So it would stop that from happening. And also, as I mentioned earlier, the AM powder feedstock can be reused. Other benefits also include the creation of more complex joint geometries by drawing braze alloys in a certain way potentially, or improving the joint strength and reducing the effects of mismatched material properties. And these can both be done by utilizing additive manufacture and some sort of topography optimization. So this sounds really cool. So why isn't it happening yet? So typical surface finish of an AM part, according to its arithmetic average roughness, which is the RA value, is between 5 and 35 micrometers, whereas the required surface finish for brazing is between 0.6 and 1.6. So there's quite a vast difference between these two values. And it also turns out that wetting on rough surfaces is much more complex than the traditional Young's wetting that I explained earlier. So it ends up being either the Wenzel state, where it fills the grooves on the surface, and this would be wetting, or the Casey-Baxter state, where there are small air pockets trapped underneath the alloy, between the alloy and the surface, and this is typically associated to non-wetting states. So a lot of the literature focuses on inducing this Casey-Baxter state for hydrophobicity applications, such as self-cleaning windows and water repellent surfaces, but we need the opposite for brazing. And a lot of the wetting research occurs in either a very, very randomly rough structure or the complete opposite in a very structured surface. So on the one hand, you've got randomly rough surfaces that are on the scale that would be still optimal for brazing. And literature here does focus on metal alloy contact and also spreading behaviors. Whereas you've got additive manufacturing, which is much more rough than the randomly rough structures that are covered in literature, are not quite as structured in terms of, well, they're not as structured as the structured surfaces that I've shown. So the structured surfaces themselves can control liquid movement even beyond the wetting stage into the spreading stage, but they're still controlled by capillary action. However, the vast majority of this research focuses on the movement of water. So this is just a larger version of the image that was on the previous slide. So between the top and bottom results, the only change is from the straight groove down to an angled groove to 45 degrees. So the very bottom right of the first image shows the extreme preference for moving the water in a forward direction, and it pins the backward direction because it's controlled by capillary action. So theoretically, this could be applicable to braze alloy systems as well. And you can even see in a much more simplistic system, which looks at the spreading of liquid over straight channels, that there's a preference for the movement in the parallel direction compared to the perpendicular direction. So how could this be applicable to brazing and additive manufacturing? So what I'm doing is hoping to study the high temperature wetting on native additive manufacturing manufactured surfaces in situ. So I'll be analysing it via tomography to look for any potential voids within the wetting system and any potential problem features or aspect ratios that might be too severe for an alloy to move over. And also looking towards the mechanical testing side of things, looking at shear testing for joint strengths. And also, because of this research shows that patterns could enhance wettability and even control flow direction, I'm hoping to use the freeform nature of additive manufacturing as an advantage, rather than having the roughness of the surface be an issue, to hopefully induce wetting or potentially promote some sort of anisotropy in the wetting flow. So these, the image on the left is an example of some of the structures that I've made. So these are very simple straight wave gratings. And hopefully I can get some results out of this. But as I say, I'm only in my first year, so I'm very much presenting a concept to you today. So in conclusion, today I have introduced to you what additive manufacturing is. So it's a layer by layer building technique that can create complex geometries. And I've also introduced brazing as a joining technique that could be used using a molten filler technique. And really what I'm hoping to do with my research is combine additive manufacturing and brazing. And this has the potential to reduce manufacturing lead times and reduce wastage. It also has the potential to create more complex joint geometries and potentially stronger joints with topography control. And there's a variety of industrial applications for this. And it really uses techniques that are already standardized in industry. So it could even be a further promotion on the two individual techniques. So that's it for me. Thank you very much. And any questions are appreciated.
Frances, thank you so much for an excellent presentation. I can see Mark clapping, and I've got no doubt others are clapping at home as well. Oh yeah, look, you can see them all coming through. People have found the clap function in the reactions button at the bottom. I'd forgotten that existed. Thank you, folks. Frances, I have questions, but I'm going to hold mine until the end, and I'm going to pass over to the judges and let them. I can already see Peter's unmuted.
I think I better let Sarah ask the first question, because otherwise I'm going to pinch you, don't I? So I'll go last, and if Sarah asks the first question, over to you, Sarah.
Right. I'm going to get straight in there then. I love the idea of using two different construction methods together. So you mentioned that you could use soldering and you could use welding, and they each had their own limitations. But could you give me an example of an application or an environment where you could specifically use a brazed construct, if you like, where soldering or welding would actually be unsuitable?
Yeah, so my research actually goes towards fusion reactors. So what I'm doing is a very specific component within the tokamak, which is like the big donut shape that holds plasma. So for that, the temperatures get too high, so you can't use soldering, but you don't want to have the microstructural damage that welding would cause. So it's a tungsten and then a gold nickel alloy in the middle to a copper heat sink. So that's where my research would really be coming into its own.
Okay, what a nice example. Thank you.
Yeah, I think it's my excuse me, that's my turn now. So I'll have another technical question. I think you mentioned the limitation of the size of the component that can be produced by EAM. Is there any limitation in terms of the brazing? I mean, how big can you go? Up to a point that it will probably not suitable to still use brazing. If you know, yeah.
Interesting. This is a good question. Hadn't really thought of it, to be honest. So there's a lot of different types of brazing. So you can do torch brazing, furnace brazing, vacuum furnace brazing. So I think so long as you've got enough braze alloy, you should be able to get up to quite large scale joints, provided it can fit in the furnace, or it can be heated up enough in its entirety for torch brazing or something like that.
Thank you.
Okay, just a question about temperature, really. Brazing, we tend to think of as a low temperature sort of operation. You know, we're thinking of brass and copper alloys and that sort of thing. And you've just mentioned the fusion reactor and the tokamak, which is, you know, presumably very high temperatures. So the question really is the compatibility of materials. Are we talking about a huge range of temperature that you can cover with this application? You know, presumably it's like filling in the gaps, is it? With the additive manufacturing component, you then fill in the gaps with brazed material, and you can obviously use all sorts of materials, I guess, for brazing. But it's not actually going to be welded as such. So is there anything there in terms of strength as well? You know, the mechanical strength of the component. Do you think it's going to be limitless in temperature range and limitless in terms of strength? Just
I would say something is limitless, but so I've got a postdoc in my research group who's looking at high temperature brazing systems that can then feed into my research. So that covers the high temperature aspect of it. And really one of the things that I want to be looking at with my research is the potential to get interlocking structures that you produce via additive manufacturing that can still be brazed together, and that will increase the joint strength. And particular, potentially, if you need it stronger in a particular direction, you could almost have like plates like that would push against themselves. But yeah, brazing can produce strength. If you've optimized the joint clearance, you can get joints strong enough that it will actually fail in the parent material. So I wouldn't say limitless, but strong.
Okay, thank you. We will watch with interest over the next year or two. Thank you very much.
Thank you, Francis, for an excellent presentation. I'm sure you'll have a few questions coming in on the chat. You can keep an eye on them, think about your answers, but we'll be coming back to any that are in there later on at the very end. Okay, we'll move on to our next speaker. Krishnand, if you want to unmute yourself and get ready to share your screen.
Okay, hello all. Thank you for attending my talk, which titled as a use of high ionized plasma to improve the surface alloying process using state-of-the-art high PIMS technology. High PIMS here is high power impulse magnetotransferring, which was originally developed at Sheffield Hallam University and the National High PIMS Technology Center.
Okay, then we're going to move on to our very last speaker for the lecture competition this evening, and that's Daniel Geddes. Over to you. I can see that you're not muted, Dan, but I can't hear you. Action is happening. He's plugging in the headphones. No, gonna have to keep talking. Oh, I knew there'd be some technical glitches. It couldn't go that smoothly this evening.
How about now?
Oh, wonderful, loud and clear.
So, thank you very much, Colleen. I even got my Sunday name there. I got Daniel. Doesn't happen very often. So, hi, I'm Dan Geddes from the University of Sheffield, and I'm here going to present to you today a bit of an overview of one of my PhD thesis chapters, which I defended this week, or last Friday as it was. So, I'm going to talk to you about novel cementitious materials, so different cements to standard Portland cements that are used for the disposal of problematic intermediate level waste. So we're talking about nuclear waste, we're talking about things that need to be disposed of in quite a safe environment, but also we're talking about things that aren't really the top end of the scale. They're not the really dangerous stuff, the fuels that you hear a lot about. These are more the things, the byproducts, the side products, things like that. Things that come from the extraction, the processing, the usage of radioactive materials and the handling and things along those lines. So first of all, I should probably say my internet's been dropping in and out throughout the day. So if it does that and you want me to repeat anything, just shout up. But as you can tell, I tend to break these things quite regularly from how we started. So so intermediate level waste, or ILW as it is known, is quite a problematic area of nuclear waste. It's not the biggest area, it's not, but it does contain the most variety and the most variation. So there are lots of different types of intermediate level waste. And a good example of this is oils. And oils can't be cemented. So cementation is the preferred method for the disposal of ILW. And we can't put oils in conventional Portland cement because that runs by a hydration mechanism. And what happens with the oil? It coats the cement particles and prevents the water from interacting with the cement by forming a hydrophobic layer. And that hydrophobic layer then stops that water getting in and you get a very minimal reaction. So we need to look at alternative cementitious systems. Now, I'm fully aware that the audience probably alternative cements are something that we don't really discuss very often. Everyone knows Portland cement, they know, and that's the grey stuff that you build a house with or you put a path down or anything along those sorts of lines. Well, there are actually loads of different varieties of cement, and this is a great figure to describe them. So these are Portland cements that we use for pretty much everything that people know with that bag of grey stuff you buy from Wix. But you come down, and where we're going to work is actually right down here on this graph at high aluminium, high alkali, but really low calcium section of geopolymer cement. So they're incredibly amorphous materials that sit, well, literally at the opposite end of the scale to Portland cement. So nuclear cements, for reference, sort of sit somewhere around here. And there's some other things that we use: calcium sulfur aluminate cements, magnesium cements. These are used in your dentistry and teeth, and when they cement things in your mouth, they tend to do this. And calcium sulfur aluminate cements can be used on varying sort of tiling applications. They're more white, so when you see like a white cement for a tiling application, they tend to fall in that range. So why would we pick something that's completely away from Portland cement? Well, these are completely different, and they go by a completely different mechanism. So you react an aluminosilicate precursor with a high alkaline soluble silicate solution, and when you react them together, you completely dissolve the metakaolin away, and then you form a new gel network. And by that, you can tailor it to the exact properties you want to gain from that material. So you can interact a silicate that may be sodium or potassium. All of my work's done with potassium for varying rheology reasons and things along those lines. But you can even use things like cesium, which is really interesting because that's a completely different waste package of nuclear waste, or a part of nuclear waste. I digress, I won't get into that really today, but that is something that is definitely worth looking at in terms of future work and things along those lines. And the other great thing about geopolymers are they offer an intricate pore structure. So on a cement for nuclear waste disposal, we don't want a really small pore structure, because if you have a really small pore structure, then then when you undergo radiolysis, which is what we'll talk about later, the samples undergo this radiolysis process and they release hydrogen gas. If the pore structure is too small, then you have basically made a bomb inside your nuclear waste repository. The Americans had a go at making that, and that went really badly for them. So we don't really want to do that as a thing. So what we're trying to do is make something with a big enough pore structure to let the hydrogen gas out. But what we really don't want to do is make it too small that this can't get in. But if it's too big, you can leach out all of your radiation. So it's really like finding a really nice envelope formulation. So we've been able to do that with metakaolin-based geopolymers. Metakaolin can be produced by rotary and flash calcination methods. And this will and what we're going to do here is examine the suitability of these materials under irradiation. So we're going to irradiate these metakaolin-based geopolymers and see what happens. So here is the irradiator that I used at the University of Manchester's Dalton facility. They've very kindly allowed me to put my samples in there for 10 days. And when I ran these samples, we decided I could have got a higher dose than I got, but it would have been an incredibly high dose rate. And there's always arguments in the literature about dose rate to total dose effects and things along that sort of line. So we picked a sort of middle of the road dose rate to get a relatively high dose of 3 megagray. This isn't a lifetime dose of the samples, but it is close and it is fairly representative. And it's also 3 times whatever anyone else has published in the literature. So this is really interesting. Gamma irradiation will show the effects of irradiation on these samples and hopefully help us to try and understand irradiation effects. So for reference to this figure here, the red samples are the flash calcined metakaolin and the white samples are the rotary calcined metakaolin. Don't always come in red and white, but it does make a really good visual for this. And the most eagle-eyed viewers will notice that I did want to put Gravian cement at the bottom here, but I'll happily take a question about that after this. It was interesting. So as we go into this, I decided to have a look at the water loss. As I mentioned, you get hydrogen release. This is from the radiolysis of water. So the thing that we want to see, the cement is the majority made up of a large amount of water. So we want to see the effects of irradiation on this water. So we've done TG analysis with mass spec, and the results are fairly interesting. So this is for the rotary calcined white metakaolin here. And what has happened is that what has happened with these samples is that fundamentally they have lost water under irradiation. This was to be expected from the samples. So this dashed dot line here is a room temperature sample. The solid black line is the sample that went in the irradiator. And then this dashed line in the middle is a sample that was heated to 50 degrees C, which is the same temperature the sample undergoes in the irradiator. So it's fairly safe to say that we've lost water here in this position. Now this is the free water. This is water within the pores. It's not in the structure. All this is really doing is filling those pores within the sample. So we've lost this. This is not a great loss from the system, but here we see on the shoulder of the curve at around 175 to 200 degrees C. This is what we call bound water. This is water that is held within the gel structure of the samples. So when it's been irradiated, if we were starting to see a loss of this water, then you really want to consider what is happening to the structure, and structural changes may be occurring. And that is what we see here for this lower water content system. Interestingly, the higher water content system seemed more stable. You do also, so if we compare the results to the flash calcined or red metakaolin, you can see very similar trend, but actually this one is a little bit more stable to irradiation. This is an interesting study, and overall it contains less water, which by definition will make it less stable, more stable, sorry. You can also see that there's a slight bump in the curve here, and this is related to carbonation of the sample. Irradiation induces carbonation. Carbonation is a worry to the nuclear industry as it can cause expansion and cracking and things along those lines. But the level of carbonation we see here is about 0.5 weight % of the sample. So that's not really too much to worry about. So what I decided to do was do some X-ray diffraction. We saw a little bit of this earlier, and it was a lot more crystalline than the species that we're seeing here. This is a very large amorphous character here, you can see, and fundamentally nothing changes within the sample's crystal structure. Now, irradiation has been shown to produce crystal structures in cement systems, but it doesn't appear to show anything in geopolymer and alkali activated materials. So this is incredibly interesting and shows that there is mineralogical stability. Now, if we flick over to the flash calcined RGSEM system, as it is known, this red metakaolin, this is incredibly crystalline in on itself, and it has large amounts of quartz in that sample. So by having this large amounts of quartz, it does appear to change. You can see there's mineralogy there, but there isn't any change in it. So let's go down to an even smaller scale. Let's start looking at the nanoscale. And I've done this by magic angle spinning NMR for the aluminium-27 nucleus. So the aluminium-27 nucleus is a key part of the gel structure within a geopolymer system. And also these samples take around an hour to run each. Silicon is another major component, but if we run that, that's a 6-hour scan. And to be honest, it costs a lot of money to run the machine for that long. And also, it doesn't show us much more data. It shows us different data, but chemical stability should be shown from the aluminium data. So if we compare these two aluminium 4 peaks, these ones that I've highlighted with the orange and green line, fundamentally nothing has changed. But you can see that the green line at the top and the orange line here at the bottom, which represent the Metamax and the RGSEM systems, the rotary and flash calcined systems respectively, there is a slight difference in that peak position. So it does show that the machine is capable of seeing small changes in the crystal structure of the material, but it hasn't seen any based on the irradiation compared to the heating of these samples. So I think it's fair to say that these samples are fairly stable under irradiation. They lose a bit of water, but their structure and their overall chemistry remains the same. So let's go and have a look at the actual sample itself. So the solid samples, and do some imaging on them. Now, this work was done at Imperial College, and you can see that fluorescent epoxy and they've impregnated it into the sample. So you've got room temperature, heated and irradiated sample here at the bottom. And the RGSEM material fundamentally has more epoxy impregnated into the sample. I'm not really going to go on any more about the porosity, because if you look at the RGSEM sample structure, you will see that it's really covered in quartz, and it's really heterogeneous. So it's really hard to pick this out using this technique. So what we're going to do is just look at the RGSEM Metamax rotary calcine product. So what you can see here are that this is a relatively heterogeneous structure with some pores here. And what we can see is that the epoxy is impregnated into these cracks. And when it has gone into these cracks, the sample itself has, the width of these has been measured using image analysis software. And we can compare the sample for the 11 and the 13 water ratio, so the high and the low water ratio. And I accept the fact these error bars are fairly large and more analysis is needed to understand fully to narrow the statistical average. However, what we can see here is that water content does affect the cracking, but fundamentally the irradiation doesn't really. They go up slightly, but they are well within the error. So there isn't massive amounts of cracking in these samples based on irradiation. This shows a really stable system has been formed. And the reason for impregnating the epoxy is that if you impregnate the epoxy pre-sample analysis, you don't get cracks like this, which are formed by the vacuum of the SEM, and they cloud your results, and you try and you see things that aren't quite there. By just analysing these are cracks that have been formed either by the actual irradiation, or they could be prepared by the cutting of the sample, but they've all been cut in the same way, so you would expect these to be relatively similar overall, all the samples. So here we can see the heterogeneous structure that I mentioned earlier, and why it would be really difficult to look at this and analyse this pore structure. So what I would like to do is do some micro CT analysis, which I've actually got booked in for next month, which would be quite nice, to really focus down on the pore structure and see if we can see changes in the actual porosity of these samples. So I talked at the start about silicon oil, and impregnating silicon oil within these samples has actually done some interesting things. So if you compare this black and blue line, these are the room temperature and heated control samples respectively. We see this standard water peak, and we see another drop at 200. Now this drop at 200, I believe, is due to the hydrolysis of the oil that has occurred within the activating solution. And then when we've irradiated the sample, this red line, we've actually reversed this reaction to a point and reformed the oil chains slightly. So this is why we get this large area of sample that appears to contain oil in this region. Now, this is only a theory, and I do need to test this a little bit more. It does fit with the decomposition of silicon oil, which is this line here. So just to conclude, I have shown that these samples are stable under gamma irradiation. Careful formulation does need to be undertaken in order to control the chemical and physical properties of these cements under the harsh conditions of gamma irradiation. So we have shown they're stable, but we really need to do a little bit more just to show that their porosity doesn't change too much and that they are physically stable. I think we've pretty much proven they're chemically stable. Oils are successfully incorporated within these cements, and that is actually shown on this Predis project that I mentioned at the bottom, which has an entire work package based around the impregnation of oil in these samples and using geopolymers for the disposal of nuclear waste. And just a bit of future and further work that I want to do. I mentioned that we use dose rate and dose and things like that. Analysis of this a little bit more, widening the formulation, showing more tailored chemistry would be really useful for this. And as I mentioned, micro CT to examine the cracking and also the porosity would be really interesting. And really nailing down what's happening to these oils under irradiation is something that really needs to be done in order to prove that these materials are safe for nuclear waste disposal. So thank you very much. Thank you to everyone on the screen for all their help with everything throughout my PhD and also in the preparation for this. And I would just like to open up to any questions.
Claps are coming in, Dan. Thank you very much. I'm sure there'll be a few questions coming in on the chat from people who are viewing tonight, but I'll hand straight over to the judges.
Okay, thank you. Yeah, an interesting problem, with this nuclear waste. Bung it in cement and then stick it somewhere, yeah?
That's the solution.
I'm not going to get into the detail of what you've been doing, but what are other people doing? Nuclear waste is a problem around the world. And there are obviously leading countries like, I guess, Japan, USA, France. Are there any learnings from what they're doing in terms of, are they looking at the same things, cements? Are they trying stuff? What's happening there?
Yep, there is a lot of cement research actually being undertaken at the moment. And I referenced a review in there that was done by the Japan Atomic Energy Agency, which was actually on geopolymer cements for nuclear waste disposal. It went into complete detail of that very small field. The French are doing a lot of work on geopolymers as well. To bring it out slightly and look a bit wider, there's a lot of work, particularly in Sheffield, on glass and on using varying things like ceramics and hot isostatic pressed ceramics, and also using different kind of absorption materials to try and absorb these radionuclides. So colleagues of mine are looking at iodine waste immobilization and things like that in resins, effectively, to then dispose of these under. We can either cement them or we can do varying other types of disposal. So yeah, there's a lot to learn from what people are doing around the world, and we need to talk to each other, probably more.
Okay, thank you very much. Where are we going now? Sarah, yeah?
I'm going for it, yes. Okay, so you mentioned towards the beginning of the presentation about having pores that were too small so that hydrogen wouldn't be able to escape, and we don't want that. And we don't want pores that are too big so that the oil isn't captured. I'm sorry if I've simplified that a bit too much, but so to me, as somebody who doesn't think about this field, who has never thought about this field before, to me it seems that you need a Goldilocks of pore sizes. How controllable and repeatable are the processes to give you that pore size?
Very much repeatable, I think. So because these materials will be made on a much larger scale than what I would make them in the lab, I maybe in the lab make them on a 100-gram scale or at the most a kilo scale. Their reproducibility between batches may be different due to mixing and things like that, and which way the wind's blowing, to be perfectly honest, usually when I'm working in the lab. But if you look at things like, if you look at how they would do it on a plant, they would have big hoppers that run in exactly the same way, in exactly the same system. They would be in-drum mixed maybe, so they have a paddle in the bottom of the drum and then mix it up that way. So everything would undergo a very similar process. So they should all be very comparable. I'm not going to say they're all the same from batch to batch, but you're not going to get something that has 10 mil pores on one sample and then 10 nanometer pores on another. I think they'll fit within a very small range.
Okay, thank you.
Thank you, Daniel, for the presentation. I have a question for you. Now, that has to do with how difficult it is to achieve and control the chemistry of the samples and also the desirable microstructure. The reason I'm asking this question is, how can you repeat the same quality and you make sure that you have this quality control? Because we're talking about nuclear waste, okay? It's not something that, like a brick, or you can play a little bit with microstructure. So you need to be, I assume you need to be very specific.
So you make the system by reacting, so you make the activating solution by reacting potassium hydroxide in a known ratio with potassium silicate. So that's a process that you can control. You can control the amount of potassium hydroxide to potassium silicate, and you can therefore, you get control over the silicate there, the potassium and any of the impurities that may be within that system, you can control. In terms of the metakaolin, these have slightly less control, but how the nuclear industry works now with cements are they pay a hell of a lot of money to make sure they get the exact same cement each time. Because fundamentally, if they pay, I'm not sure the exact figure, but if they pay £1,000 a kilo for the cement, which they definitely don't, but if they paid that in the grand scheme of the lifetime cost of the package, that's nothing. So they pay large amounts of money to make sure that what they get is consistent each time. It might not be the best solution, but it's very consistent. So as long as you can control the precursor and the activating solution in my system, then you can definitely keep producing the exact same microstructure each time and the exact same gel structure each time, which is exactly what you want. To be honest, this system is very flexible. You can alter by quite large amounts in order to get a relatively similar structure. So there's plenty of error there to be working with.
Thank you.
Thank you very much, Dan. And a big thank you to all of our judges this evening who have taken time out of their day and doing a little bit extra work to come along and not only look at and listen to these very different subjects, but then to find questions that were challenging to each of the contestants who in their own rights are experts in that field, and you guys aren't. So I'm very impressed. Well done. I'm glad I wasn't on the judging panel tonight. I have got questions though that I'm going to save. The judges have got a breakout room that I have made you. I'm just going to open it now. So you should have received a notification, you three, to say, jump into this room. And that will give you guys the chance to discuss. While the judges are in there, I need to get rid of things so I can see. I'm going to hand over to Mark Tomlinson, the Secretary of the SMEA, and Andy Woods, the SMEA President, to present our student prizes. But perhaps actually we should do questions first. What do you think, guys? Mark?
Yeah, that sounds good. I think we'll have some questions first so that these guys can get it all over and done with.
Good idea. Okay, then we'll hold the student prizes for a moment or two. So Henry, you're going to be on my hit list for coming on to the judging panel next year. You've asked a question to every single participant. Perhaps you want to unmute yourself and throw a question at one of the contestants. You don't have to.
Okay. For about the brazing, you need to produce when you're brazing, you need to produce a wetting on both materials, I guess. That whereas as we've found with soldering, whereas if you're welding, you need to the two elements, the two components have to melt and produce a fluid between them that they've got to mix properly. That's not necessarily the case. You could have two materials that wouldn't, but when you're brazing, you don't need to have the two materials that will actually would actually melt together.
Yeah, that's exactly right. So for welding itself, you can use filler metal, but it's not as common. But typically it is melting two materials together. But for the application that I've got, it uses tungsten and copper. So they've got very different properties, and especially their coefficients of thermal expansion are significantly different. So if you try and weld them together, you're just going to form lots of cracks when you try and heat it up. And then obviously soldering is completely out because you've got the temperature issues of what temperature a fusion reactor would get to. So brazing really is that middle ground that my sponsor has found most applicable. And so I'm looking to get potentially get the tungsten and the copper additively manufactured, and then joining the two, or potentially just looking at one. And that will also hopefully help with the mismatch of the thermal coefficients to basically improve the joint strength.
Yeah, good.
Thank you very much, Henry, for your question. Mark, I'm going to go to you. On your XRD, in the top two traces, you showed what I assume is an impurity. You had the little diamond on it, but you didn't tell us what it was. So what is your impurity there?
Good question. We think it's some unreacted. I lost it. Unreacted oxides, still there in the sample, basically. Sorry, I just zoned out.
That's okay. Francis, there's another question for you in the chat from Ajay Westnedge. What materials are you brazing together?
So at the moment, I am using a 316 steel, essentially because I can get it to print via AM, and so I can actually get to trialing the surfaces. So that's where I'm starting at, and I'm using a silver a set of silver braze alloys that all have different flow properties. So I'm trying to see if something with that has a high flowability will be able to move across a more rough surface better, or if something that's really stodgy that might not get caught up in like a void or something would be better. But then, yeah, I'll be moving on eventually to trying to print tungsten, which will be a challenge in itself. And then using something like a gold nickel alloy, I think, is what my sponsors will be looking for.
Brilliant, thank you very much. Geddes, I'm sure I saw a question for you in there. Can't find it. Krishnan, you've just put a question in the chat. Who's it directed at?
Yeah, it's for Dan. So basically, I can see that your surface is very porous, right? And what I believe is that porosity is influencing the crack formation and the growth. Did you try to measure the porosity and how they are, I mean, in terms of size and depth and what? Did you do that? You are mute.
Every time on mute. No, but I will do in about 2 weeks' time when I can get access to the instrument. I've been trying for nearly 2 years to use a micro CT to measure these samples, and I've finally got the instrument access to be able to do it. So yes, in answer to your question, hopefully that's the answer.
Okay.
But we'll see. We'll see. So I found the other question, Colleen, if you want me to jump on.
Yeah, do please.
So it's how safe is nuclear waste containment with modern technology compared with the original nuclear plants? So not my area of expertise by any stretch of the imagination, particularly when it comes to how a nuclear reactor works. However, they are much safer now than they definitely ever were. And particularly any incidents which we all see about on the news and things like that will make them even more safer, because you can't go through a system that, for instance, reacts badly to a tsunami. That won't happen anymore. There will be a barrier put in place. It's the safest industry, I would say, that I know of anyway. So they are safe to the point of getting slow, if that makes sense to anybody. It's a slow change because everything has to go through rigorous safety procedures. And as I mentioned about in answer to one of the questions, because the specification of cement powders they use, for instance, is so tightly controlled that it actually means that moving off that is incredibly difficult. You have to prove it's as safe or better. There is another question there, or there's a comment from James that says cement is boring. And I just need to draw the attention to Antonia's comment that it isn't boring, it's just misunderstood. And well, we could all say things about glass, James. We could all say things about glass.
Okay, I'm going to open the floor up, see if we've got any questions that people might want to vocalize.
I've got one, if that's all right.
Yes, please go for it, Mark.
Yeah, Dan, it's for you. You mentioned you worked with potassium specifically because of rheology properties. Could you expand on that? I know obviously alkali metals are all quite soft, but why potassium specifically?
So potassium silicate the potassium silicate activated systems have a much lower and much more controllable rheology than their sodium counterparts. Sodium and potassium silicate are the two major used systems that we have the data for so many systems. Potassium nowhere near to the same level of sodium, but the potassium it just flows a lot more, to put it into a simple term. The difference being you could pour one on a table and the sodium would stay there in sort of a lump or a kind of cone, and if you poured the other one on the table, it'd run on the floor. So that's the sort of difference we're talking about.
Gotcha. Cheers.
Let's see if anyone else jumps in to ask.
Okay, I'll ask a question for Krishnan. Krishnan, you talked about the interpreting the mechanical properties from your micro hardness indentations. Could you just talk a little bit about the relation between the size of those layers and the size of the indentation, and how you think those things interact?
So basically, this formula which we use, it's ideally developed by the, I think, theoretical mechanical people to analyze only thin layers, thin film, I would say, in specific. So what it does, it has a factor which is basically inversely proportional to the fracture toughness, which is, I'm talking about the crack length. So this crack length is individually doesn't contribute to the formula, but it contributes with the diagonal length. So means you are measuring from the center of the point to the diagonal and adding plus the crack, if there is a crack, which is, I think, pretty much same in when even we do with the notch type of, right? So we just hammer it and we see how long is the crack length. It basically does the same. The only thing here we are considering the factor of thin film instead of the base layer. Yeah.
Okay.
And it's frankly, it's pretty much straight formula. I mean, if you go through ASTM standard, it's quite confusing. But if you follow this, you can get it easily.
All right, cool, thank you. Francis, it's interesting to see what you were developing there. You thought about trying to incorporate some other technologies that might be a little bit older. It'd be interesting to see whether some nice woodworking joints would be able to be infiltrated with braze and give a better mechanical solution. You think that's possible?
That's a really interesting thing. Yeah, I'll be honest, I haven't really considered it. But it is, yeah, because it's the sort of interlocking joint, isn't it? Yeah.
Stunned her into silence there, I think.
So I'll probably be looking into that. Thank you.
Good. So, Mark, there was a question in the chat earlier, I think one of Henry's, that just asked what the you talked a lot about the Curie temperature, and what is it about the particular capacitors applications that mean you're searching for a higher Curie temperature?
Right. So yeah, I mean, so any industrial electronics would use ceramic capacitors, including some of the ones I mentioned. So oil and gas industry, even during the exploration itself, drilling, these all have capacitors as well. Power electronics, etc. Avionics, military applications. In terms of the Curie temperature specifically, so just reading Henry's question here, where are high temperatures important with capacitors? Yeah, I've answered that. You actually seem to reduce Curie temperature by adding calcium. How does this work? Excellent question, thank you. So the calcium in this case, from the very last image I showed, which you probably forgot by now, but it showed an ever slight decrease, like you said, in the Curie temperature. But I was just aiming at showing you that we can alter the Curie temperature as opposed to you can increase it or decrease it. In terms of some of the industrial capacitors that are used, some of them actually would decrease that peak and increase another peak before. You saw there were 3 peaks, one at 125, one slightly below room temperature, and one in the negative regime. So some peaks are actually, they come closer together in order to smooth out. So lowering the Curie temperature does actually work in that sense. But also, it's the case of that calcium specifically decreases, but you could also equally dope with something else and increase. So this is just kind of giving you an idea of that you can change it, as opposed, I wasn't aiming for specific increase with when I showed you this.
So is there a gradual effect on the capacitive power of the capacitor as you approach the Curie temperature?
Yeah, so the reason you get that peak, so it's a bit weird. So we say that in the tetragonal phase, before, when the titanium is still offset, before it goes to cubic and it's stuck in the middle, you actually notice a huge peak of capacitance. So where does that coming from if the titanium basically moves towards the middle? Well, in order to transition from tetragonal to cubic, the atoms distort and they move around a lot, and in doing so the titanium actually offsets even further, and then before finally returning to the cubic position. So that explains the peak there. So, and that again is a very clever way there's a field of study that kind of cleverly exploits that by taking that higher peak and relaxing that, broadening over a phase of temperatures. This is called ferroelectric relaxers. Very, very interesting.
Thank you. And lastly for Dan, before we get to our awards, you talked about this encapsulation with cement, and you talked a lot about the long-term stability of that to irradiation. Is there are you considering the cement as a entirely inert material, or is there a companion piece of work looking at the reaction between the cement and the oil content with the material that you're actually encapsulating?
Yes, so fundamentally it's a very tricky topic, because the system will continuously react, and these things will happen. You have incredibly high pHs, which will affect the pore, affect the oil, and things along those lines. We have a new PhD student starting in Sheffield in September that is going to be solely focused on carrying on what I've done with a focus on the oil application specifically. So that was meant to be a large focus of my PhD, and actually turned into a relatively small chapter at the end. So I'm hoping to be part of that project as well, to drive that forward and hopefully look at the long-term effects of the activating solution on the oil, the effect of the irradiation on the oil. So I think specifically we need to take the oil, the activating solution, and the pore solution that's post irradiation, and see how all of these things interact with each other. If that answers your question.
That's great. Thank you very much. I think it just remains for me to add my thanks to the thanks that have come up in the chat. I think all the presenters have been fantastic this evening. We've had such a wide range of materials, some really excellent slides, a lot of very confident delivery, a lot of expertise shown both in the presentations and in the response to the questions. I think you should all be very proud of yourselves. I think particularly so as we're all grappling with a new platform for things like this. You've not had the benefit of lots of years standing in front of dull rooms full of people to fall back on. So to be so competent and enthusiastic for these presentations has been really good to see. I'm glad we had a little bit of a technical problem. I think is it even a Zoom meeting if something doesn't go wrong? So I think you've all done really well. The only advice I would give you is to try and maintain that enthusiasm that you have shown for your subjects. That will stand you in good stead throughout your careers. I think you can see by the questions that we've had that material science is a good thing to keep your enthusiasm going for many years, and so I'm sure that's something that you can build on. So thank you for your entertaining talks, and good luck. So we'll now move on to the awards that we give out. Now, ordinarily we would do these at our annual dinner, and the winners would get a meal out of it at least. Unfortunately, that's not possible this year, but we did think it was important to continue acknowledging the performance and the success of the best performing students at both Sheffield University and Sheffield Hallam University. So I will pass over to Andrew Woods, who will announce the winners.
Okay, thanks, Mark. First of all, I'd like to add my thanks to the 4 presenters. You've all done an excellent job, and good luck to you all. I think Zoom's a bit more daunting, to be honest, than a room full of people. But yeah, it's a good experience for sure. So one of my first duties actually as incoming president of the SME is to do the awards presentation this evening. So it gives me great pleasure. So the first award is for Industrial Project Prize. And that goes to James Knight. Well done, James. James, I see you're online. Would you like to just say a few words about what the project was about?
Yeah, thank you very much. Can you hear me?
Yeah, we can. Yeah,
Excellent.
loud and clear.
Excellent. So yes, it was last summer. I managed, in spite of coronavirus, thanks a lot to Forge Solutions Group, I managed to get down, well, from my house in Sheffield, still in Sheffield, but I got across those few miles and into the office and onto the shop floor to be able to work, do some work with them on a couple of projects. One with Arash Salahi on the heat treatment furnaces and looking at optimizing. Unfortunately, their order book was a bit down, as I think everyone can imagine. So it was looking at trying to do a bit of short-term cost savings there. And then a second project over at the River Don site, looking more at kind of a bit more of a technical side of things, a bit more materials involved there, and sort of going into more the processing route, and particularly on the forging furnaces I was looking at. So it was heating the parts up before the first forging step, ensuring that it's heated all the way through, and looking to see if there was some efficiency gains that could be made there and product quality improvements. So that was my project that I managed to get in the 8 or so weeks that I was able to get on site. Thank you very much. I'm very grateful for the award. It was completely unexpected, so thank you.
Okay, well done, and thanks for the summary. The second award is the prize in aerospace engineering, and that goes to Daniel Pickering from the University of Sheffield. I believe Daniel's also online, so well done, Daniel. Great achievement. Then the rest of the awards I'll read out. Unfortunately, the guys haven't been able to attend. I've suggested to Colleen for future events we could probably do a live video stream, to their holiday homes in LA, a bit like a real awards event, but we'll see how that goes, but maybe a thought for future years. So the Hatfield Memorial Prize in Metallurgy goes to Rohan Dunnett from the University of Sheffield, so well done to him. The Hatfield Memorial Prize in Engineering goes to Jonathan Jackson from the University of Sheffield, so again, well done to him. The Hatfield Memorial Prize in Materials Engineering goes to Judith Gulpin from Hallam, and that's awarded to the top final year students, so that's a great achievement, so well done again. The SMAA Prize, Hallam awarded again for the best dissertation, goes to Berwyn Owen Pollard, so well done again. And then the Hatfield Memorial Prize in Materials Engineering, again Hallam awarded to the top student on level 5 of the BEng BSc, goes to Joseph Edward Clayton, so again well done. So well done everybody who's won awards, great achievement. Okay, so Mark, is the plan now that the judges will reappear?
I'm hoping they'll reappear with some fanfare, but I can't imagine their names on the list just yet. I'll try some other technology to get hold of them.
Yeah, the technology of these breakout rooms is something else.
I can find that room. Right, so from what Colleen was saying, it looks like we'll be looking to host the regional finals, and then we can go on. It looks like our judges have reappeared. So without any further ado, Colleen, do you want to take over?
Thank you very much, Mark, for holding the fort. I did think I needed to jump in and whip the judges along, but they had already come to their conclusion. So I'm going to ask Peter Morgan to tell us who the winner is.
Right, okay. Well, first of all, you guys don't make it easy for the judges, do you, eh? Every year it's like this. We always struggle to try and decide who's come out on top. Very good presentations from everybody. Interesting topics, quite diverse topics, quite different topics as well. So, you know, a lot of credit to all of you. So thank you very much. What we're going to do is we will just announce the winner rather than a 1, 2, 3, 4, because we don't think that's fair. And what we have said is that if any of you want any feedback on your presentations, then the judges are more than willing to have a word on the phone or whatever. If you want that, and if you contact us through Colleen, then we can offer that. Normally, we would do that over eating chips and salad in the Holiday Inn in Sheffield, but you know, we can't do that. So we feel that's a bit missing. So you know, if you want some feedback, then by all means, please get in touch. And let me go straight for it. So first prize, which is going to be a cheque for £150, plus also going through to the next round, is Francis. We thought Francis's topic was very interesting, novel, innovative, so very, very interesting, but a fair way to go, because you haven't got a lot of results yet. So we're putting a lot of faith in you, and maybe a little bit of adjustment with perhaps some examples of potential applications might be good. But you know, in going forward into the next round, if you want any help, any guidance that we can give it, we're more than willing to do some feedback. So you will get a cheque for £150, and we will ask you to go into the next round, whenever date that is, so we'll be in touch. We have chosen a backup if needed, but we hope that you can go forward. And for all the other people, the other three, you won't go home empty-handed. You will also get cheques, but for £75 each. So very well done to you all. I hope you've enjoyed it. I've certainly enjoyed it. It stretched me a bit, I'll tell you. So thank you all very much. And now over to Colleen.
Thank you, Peter. And I need to say a big thank you to the whole team who's made tonight possible. It's not just me putting it together, it's getting the judges on side who give up a lot of their time to make this happen, but also the speakers. You guys have to put the most effort in. You've got to think about a topic, send in your abstract, write a presentation, and then you've got to practice it before you even get to tonight. And you've all done a sterling job of polishing up and giving superb presentations that I expect will go on to be given at conferences virtually or perhaps in group meetings. But you can definitely recycle the material that you've shown us this evening. I will say to any of the young people who are on the call who aren't yet members of the SMEA, you can join for free. You can just need to go to our website, SMEA 1894. You'll find the details if you Google that. But also we do have our professional development fund. So we're no longer giving a travel award this year. We've changed the scope of that a little bit. So if you've got a workshop, a course, a conference, or something you want to go to that's going to help you professionally develop, fill in our application form and send it back to me. So if anyone's interested, you can email me at events.smea, and you can find those details on the website as well. Unless anybody else wants to say anything to close, our next meeting is on the 9th of March, and hopefully we'll see some of you there, 6 p.m. Follow us on social media to find out more.
Thanks a lot, Colleen. And I suppose I speak on behalf of all the speakers in congratulating Francis, and then thanks for having all of us tonight as well.
Yeah.
Yeah, thank you. It's been such a good experience, because presenting online is something that's really scary to me, and you guys all did such a good job as well. So well done, everyone, and thank you to Colleen as well for mentioning it to me. It was offhand in a training session that she was giving to me that she was like, "There's this lecture competition going on." So yeah, thank you as well for hosting it tonight.
My pleasure. I'll hang around if anyone wants to chat for a few minutes about anything else that's going on in the SMEA, but hope you all have a pleasant evening and enjoy dinner and a glass of wine. Sorry the SMEA isn't providing it tonight, but next year we will. Night night, folks.
Thank you.
Cheers,
Bye-bye.
Have a good one.
Bye all.
Cheers, everybody.
Bye.